Hi everyone, I'm Giulia Guidi, and today I'm going to talk about our latest work in which we investigate the performance gap between HPC systems and cloud systems. And in particular, we focus on AWS cloud. It's interesting to see how today high performance computing HPC is seeing a new dawn. And this is because of the increase in the amount of data that we need in many computational sciences and in the new fields like data analysis and machine learning. So today HPC is not only about simulations, but there are many more disciplines that need HPC like computational resources. If we look at the brief history of HPC in the cloud, so like people have been trying the past few years to run scientific application in the cloud. And what we can see is that from 2010 to 2018, nothing really changed. All these studies have identified the lack of low latency network as the main bottleneck to run scientific application and in the cloud. Then they don't always agree on the virtualization overhead and performance variability, but I believe this is mostly due to the settings they run their experiments that can really change. But the important part is that the lack of low latency network is a limit until 2018 to run scientific application in the cloud, to do traditional HPC in the cloud. So what's the situation today? And this is exactly what we're gonna talk about. And today, in a nutshell, the result that we found is that we can confirm that computational intensive applications still greatly benefit from the cloud, especially due to the newer hardware. But what's truly interesting about this work is that we have seen that cloud performance for communication intensive and memory intensive application have greatly improved. And this is a very nice result, especially because if we look at the network performance, we can see that not only, again, the newer hardware can guarantee like greater processing powers for communication intensive, for computation intensive and data intensive application, but also for communication intensive application, we have seen better communication performance in the cloud than in HPC systems. And we ask ourselves, why did this happen, right? And we believe that this is intrinsic in the way, in the purpose of HPC, traditional HPC and cloud. And especially if we look at the reason why, the way HPC system and cloud system are configured, we can see that in HPC, traditional HPC, usually we have a particular research community, while in the cloud, the configuration follow the market demand. And this is exactly the reason why we believe today's cloud is doing a much better job in terms of network latency. And it's to keep up with the fact that there is a growing commercial interest in large-scale machine learning training. And so they have adapted, we believe, the configuration to allow machine learning to be run efficiently on the cloud. And this, as a byproduct, benefit other computational sciences and more traditional HPC. Another main difference between HPC and the cloud that is important to highlight is the fact that usually traditional HPC is a large scale, homogeneous hardware. Maybe there are 2-3 partitions, but no more than that. While in the cloud, we have very heterogeneous hardware and that is frequently updated. And this can kind of limit the large scale application that we could run in the cloud, because it might be hard to get many instances of the same time. So the way we investigate this gap is to select 2 kind of experiments. So hardware and system, where we look mostly a single node except for the internode communication. So internode and single node performance using micro benchmarks. And then once we have understood the differences between the machines at the single node level and network level, then we move to the user applications. This is the most interesting part, but it wouldn't make sense to look at that without knowing what's going on at the single node level. And for the application, we selected 2 well-known applications from scientific computing that are the embodied simulation that is known to be compute intensive, and the fast Fourier transform, FFT, that is a more communication intensive application. These are the 4 machines that we have been using, 2 HPC machines, There are like core system and both partition, Haswell and KNL, and 2 cloud instances from AWS, the R5 and the C5. And the main things that we can notice between these 2 groups is that the cloud instances are much newer than the HPC. Then we will go into the details of the results in a little bit. Here's a few more like settings that are important to highlight, especially the fact that we run the instances as dedicated instances, so they're not shared, and we place them in the same placement group to guarantee the lowest latency network we could get. So if we look at the results, so the meat of the talk, we can see that from the looking at the processor power, so in this case, we are using the LIMPAC benchmark, we can see that Haswell and the cloud instance R5 are very close to their theoretical peak. So this is good. While if you look at KNL and C5, they have much harder times to get to the theoretical peak. For KNL, there have been like many studies in the literature that have shown that it's difficult to get to the top, to the theoretical peak with this kind of processor. For the C5, we did some further profiling and saw that there is a low core utilization that could explain why we cannot get closer to the theoretical peak, but this in particular would require more investigation. Overall, what we are interested in, the takeaway of this plot is that cloud's faster procurement cycles, like into the newer hardware, can explain the greatest processor power, and so can greatly benefit compute-intensive application. If we move and look at the memory bandwidth, we can see that, and in this case, is the stream benchmark. So it's important to point out that data cannot fit into the cache. So this is the measurement of the whole, of the entire memory system. We can notice that KNL is doing a much better job than the others, and this is because it has an on-chip memory. If we look at the 3 other processors that don't have on-chip memory, we see that the cloud instances are doing a much better job than Haswell. And this again is in line with what we have just seen for the processors, like newer hardware, like faster procurement cycles can get newer hardware, and this can benefit compute-intensive workloads and data-intensive workloads as this memory bandwidth can show. If we move at the inter-node communication, we can see that, for example, like we have, what is interesting to see here is that we have, so core is a host, like a single system. So it's the same network between KNL and Haswell. And so one might expect the same performance between the 2, but this doesn't happen. And we believe that this is because the overhead of MPI penalizes the lower frequency cores of KNL. So what we can see besides this detail is that the gap between Corey Haswell and the cloud instances actually increasing the number of nodes. That is not what we would expect initially. What we can see is that like C5 is not doing as good as R5, and this is believed that since C5 is a compute optimized instance and not memory optimized as R5, the network is not as good. And also, if you look at the settings in one of our previous slides, the C5 has a lower advertised network bandwidth. So this result is not surprising. But what was surprising is that R5 in general and C5 are doing a very nice job overall with respect to HPC system, while like a few years back, this was absolutely not the case. So this is already a pretty good result. So now that we have looked at the macro benchmark, it is interesting to see how this applies to the user applications. Here's like a brief summary of the main characteristics of our 2 applications. So we have N-body simulation on one side and FastPeriods on the other side. And as we have seen, N-body is a compute-intensive application with a low communication to computational ratio, while the FastPeriods transfer is the opposite. First of all, we look at the single core serial performance for the 2 applications, just to make sure that nothing, weird goes on like at the single core level that might kind of, bias the multi-node implementation. And what we can see is that overall, the results are pretty similar and what we expect. And the only outlier is Corey Canal, and that can be explained by the fact that Corey Canal cores have a lower frequency, and that L2 is shared between two cores. So these results are not surprising. And so if, like in the multi-node results, we want to mainly focus on Haswell, R5, and C5 for the comparison. And what we can see here, so we have the strong scaling of the MODI on the left and FFT on the right, is that, for example, for the embodied, this is the compute intensive application, we can see that the cloud instances, the two on the left as pointed by the arrows, are doing a pretty good job. And this is in line with historical results, but it's also interesting to notice that not only the computation goes down for cloud instances, but also the communication performance. So this is in line with historical results, but it's still interesting to point out. Well, if we move to the FFT, this is the truly interesting results, because we can see that the R5 specifically is doing a much better job than the HPC instances, both in computation and communication, especially when increasing the number of nodes. So this is like an overturning of the results in the literature. So here's a summary of our results. We have seen that cloud computing in like AWS in this specific case made a significant improvement in network performance and overturning the historical results, especially for communication intensive application. Of course, this works as a few limitations. First of all, the first things we would like to do as a future work is to run larger scale experiment, because the scale of these results is relatively small, but still interesting. And then it would be interesting to widen the set of workloads and cloud providers. Also have a closer look at the performance variability. We didn't really see any big performance variability, but we didn't spend too much time studying that. And also, it would be interesting to see how we can use these results to build better HPC system in the cloud and not. Thank you very much for listening, and I really hope I will get a lot of questions during the live session. Thanks.